So, welcome back to our video lectures on projective geometry. Believe it or not, but this will be the last video slot in our series of projective geometry video lectures. It will not be relevant for the examination, it's a kind of bonus lecture, but nevertheless I think it's an interesting one and also somehow a little bit a fun one, because we will encounter several connections of hyperbolic geometry to even things like art. So art and mathematics meet in many interesting places, and this is one of the most exciting ones. So the lecture will be a two-part lecture. It will first of all deal with triangles and the area of triangles. Then we will use what we learned about triangles to draw interesting conclusions about tessellations. These are kind of mosaic-like patterns of single tiles that you can, for instance, also form in the hyperbolic plane. So let me start with triangles and their areas. And what you see here is the headline says triangles and angles. And actually the angles at the corners of the vertices of a triangle in the hyperbolic plane have a lot to do with their area. So I prepared a little experiment here. So I've drawn a triangle in the Poincaré model. I've measured the angles in the points of the sides that meet in that point, and I added these angles. And first thing you should observe here is they don't add up to 180 degrees like triangle in the Euclidean plane would. And if you remember our hyperbolic history slot, there was some statements that the parallel postulate is equivalent to the statement that the angle sum in a triangle is 180 degrees. And you see here, this does not seem to be the case for a hyperbolic triangle. So let me move the points around a little, and we'll watch this sum of the angles, and you will see that it's always lower than 180 degrees. So here I'm drawing a reasonably big triangle, so it occupies a big portion of space in the hyperbolic plane, and you see the bigger the triangle gets, the smaller the sum of the angle gets. So let's do the contrary. Let's draw a triangle that is reasonably small. So let's take our points and move them close together, and I guess you already have an idea what's going to happen. So the angle sum for a small triangle will be closer and closer to 180 degree, and the reason for that is that a small portion of the hyperbolic plane actually looks like a Euclidean plane. So in the limit case, if you focus on an epsilon neighborhood of a point, then the measurements there will look like a Euclidean measurement. So let's move the points even closer together to see that you can get even closer to the 180 degrees. And now you see I'm pretty close now. So let's do the other extreme. Let's draw very big triangles here. So let's take one of the vertices and move it to the fundamental conic. So essentially you move it to infinity. You move it as far away as you can if you walk in your hyperbolic universe, and you see that the angle at such a point becomes 0. Why is this the case? Well, in the Poincaré model, we had two important things. The lines were arcs that correspond to circles that are orthogonal at the fundamental conic. And we also had the fact that we can really read off the angle by measuring the tangent angles of two circles. So if you now consider the angle of your two sides here, this one and this one here, both have to meet orthogonal at the boundary if they have their intersection point at the boundary, and they obviously leave this point here with the same limit angle, 90 degrees, so the angle between them is just 0. And we will later see that such triangles with some of the angles being 0 are very relevant if we want to build up the general theory. So let's move one more of the vertices to 0, and let's even move the third one to the situation where the angle becomes 0. Then we have a very special triangle. In a certain sense, this is the biggest triangle you ever can have in the hyperbolic plane. Each of the angles here is 0 degrees, and the triangle cannot become bigger. And actually all these triangles with well, having all vertices at infinity are well, isomorphic in a sense, because you remember the hyperbolic transformations were completely determined by the images of 3 vertices at the boundary, and by a hyperbolic transformation you can move these points at the boundary to any place you want. So essentially you can say, well, I move this point somewhere here and this point somewhere here, and this will be just a hyperbolic transformation. So next thing we want to do is we want to get away from that experiment and insert a little bit more mathematical rigor here. And for that, the first thing we do, we switch from angle measurement with respect to 360 degrees. We switch to a full angle of 2 pi and measure angles now in radians. And what we now consider is the so-called angle defect. And the angle defect is the number that you get when you subtract the sum of all angles from the number pi. And remember, pi corresponds to 180 degrees. So why is this number so important? Well, in a certain sense, it measures the size of a triangle. And let's first consider that just qualitatively, and later on we will see that even quantitatively this is the case. So actually what we get here, if we insert one more ingredient, is actually the area of the triangle. So let's first deal with it on a qualitative side. So let's take again our triangle, and here I calculate the angle defect, and as a first thing let's make it well, reasonably small. So here you have a medium-sized triangle, you get some number here, and now let's make it smaller. And you remember, small triangles have the property that the angle sum is 180 degrees. So you get in radians an angle sum that is close to pi. So if you subtract that from pi, you get a small number. So small triangles have a small angle defect. In contrary to big triangles, so let's make this triangle here bigger and bigger by moving points to infinity, and now let's move all points to infinity. Then we know all angles are 0, and the angle defect is as big as pi itself, and in between there are all other triangles. So the area of a triangle is somehow biggest in that case and smallest in the case where your points are very close. And if you look at the angle defect, it's biggest in that case and smallest if the points are close together. So it seems to make sense. So Again, observe that all these infinite triangles, these extreme triangles, are equivalent and that the angle effect does not change here. And now we will focus on triangles with a very special property, namely those where two angles are 0, so the points are at infinity, and one has some other angle. And here let me first show you one more special case that is relevant. So if the third point is on the segment joining the two infinite points, then the angle here is also 180 degrees, and so also here the angle deficit is extremely small, and if it's really on the segment you will really have an angle defect of 0. This will be one of those cases where you really have 180 degree sum of the angles, 0 plus 180 degrees, and you see also in that case the area is 0. So next thing, we take this point here and move it to an arbitrary position, and we want to make a statement about the area of such a triangle. And for that we consider several things now. So what we are heading at is the following thing, that the area function of an arbitrary triangle is completely determined by our behavior of the hyperbolic plane and by the fact that we want to have an area measurement that is additive. So if you have two areas and place them next to each other, the area of the entire figure will be the sum of the areas. And one, I would say, arbitrary definition by saying that if we have a triangle with all angles being 0, then we define this area to be pi. And we will see that from these two facts the area function is completely determined. So how do we do that? So next thing we are heading for is a function, I call it little f of alpha, which should describe the area of this region of a triangle with two angles being 0, and we already know the value of two entries alpha. We know that if the angle is 0, so if alpha is 0, then by definition we would say, well, this triangle here should have a size of pi. And we also know a different case. We know that if the angle is pi, then the area should be 0. So the bigger the angle, the smaller the area. And what we're actually going to prove is that between these two extremes we have a linear function that simply is pi minus alpha that approximates between those two values. So now we have a really continuous situation, and in that continuous situation we want to somehow understand how this function here behaves, and we have one more ingredient. We have additivity, and to bring additivity into the game we do the following thing. We consider the area of two triangles next to each other. So essentially we're considering the area of a foregon of a quadrangle with 3 vertices at infinity, and then we have two other angles here. So you see the brown triangle here has an angle alpha, and the blue triangle here has an angle beta. And now we take additivity into account, and we dissect this foregon here in a different way by cutting it into triangles in this way here. So here, so you agree brown and blue must be the same as green and red, because it covers the same area, and area should be additive. And then you see here, well, essentially the red area is one of the biggest triangles that we can have. So it has pi, all three vertices are at infinity, and the green area is coming from a triangle with two vertices at infinity, and one of them having the angle alpha plus beta. So if we take these two pictures into account, we get the following formula. We get that f alpha plus f beta must be pi plus f alpha plus beta. And so you see we get a kind of functional equation between the area and the angle, and now from that we can conclude that it must indeed be a linear equation. And perhaps the easiest way to see that is the following. Take this equation here, and both on the left and on the right side form the derivative with respect to alpha. So if you form the derivative of this side, well, this term here, the f beta, is just constant, and what you get here on one side is the derivative of f with alpha in it, and here you have on the other side pi is constant, and this here is just the shifted function, so you get the shifted derivative here. So by calculating that, you see that the first derivative of that function is the same if you evaluate it at alpha or at alpha plus beta for an arbitrary beta, which means that this derivative is constant, which in turn means that the function must be a linear function, and the only linear function with these two fixed values is the function that I've written down here. It's pi minus alpha. So we did a lot. So we now really understand the area of triangles that have 2 points at infinity and one free angle. And now the next trick is to reduce a general area to this special case. So we know we have this situation here. This little f of 0 is pi, little f of pi is 0, or more generally, little f of phi is pi minus phi. And now assume we have a green triangle here with angles alpha, beta, and gamma, and consider the following figure that I've drawn here. So you take this side here and in one direction extend it until it meets infinity, and you do that for all the three triangle sides. So you get a big triangle, which is one of those with all angles 0, so we know its area is pi. And then you get three small blue triangles here, and each of these small blue triangles is of the form that we just studied. So here at these places you get angles that you actually can measure, and they are the counter angles of alpha, beta, and gamma. And so you see the area of the green part here must be the big triangle minus the three blue triangles because of additivity. So you get the area of the green triangle is f0 minus these little f functions, where you have the counter angle of your angles here, and now the rest is a piece of cake. So you just insert what you get, and what you get is exactly the formula we want to have, that the area of the green triangle is just the area of this one which is pi, minus the area of this one, which is alpha, minus the area of this one, which is beta, minus the area of this one, which is gamma, which is exactly our angle defect. So all in all, we can put everything together and really see that the angle defect does not only qualitatively relate area and angles, it really does it quantitatively. It is the size of a triangle. So you see, well, you have interesting triangles in the hyperbolic plane which completely behave different from Euclidean triangles. And at that point, let me now first compare that to the situation in spherical geometry and actually what happens there. So assume that you have a triangle on the sphere given by arc segments. So we see that also corresponds to a certain Cayley line geometry. And what happens here is that the sum of the angles will always be bigger than 180 degree, and you can define something like the angle excess, which is well, the number that you get if you subtract pi from this number that is bigger than pi, and actually this measures the area of a triangle on the sphere in the same sense as the angle defect measured the area of a triangle in the hyperbolic space. So just to make a comparison, if you have a unit sphere, it has an overall surface of 4 pi, and let's do a little experiment. So let's take the sphere and cut it into 8 equal pieces, and I did so here by taking 3 mirrors and having these 3 mirrors placed in a way such that between 2 of the mirrors you have a 90-degree angle for any pair, and so you see this eighths of a sphere that you have here makes the entire sphere. And now let's compare what you get here. So the area of one of the octants is, you get 3 times 90 degrees, so you get 3 times pi over 2 minus pi, which is pi over 2. So the area of that triangle here should be pi over 2, and if you have 8 of them, they really all together make the area of the sphere. So you see, everything is pretty plausible in that way. So I intentionally introduced mirrors here, and you see that I had 90-degree angles between these mirrors here, because the next thing I want to talk about is called reflection groups. And for that I first have to talk about angles a little bit, and I want to talk about what I call good angles for reflections. And here I have again a real world experiment. I've placed 2 mirrors in that picture, and I have some scenery here in this angle formed by those 2 pictures, and you see how if these 2 mirrors are in a good angle with respect to each other, where good angle really means between them you have 90 degrees here, then you get a perfect picture of 4 times your scenery. Here I have a little more an abstract version of that. So here are my 2 mirrors. I have a 90-degree angle, and you see if I move my object around, you get 4 perfect copies of that. They may be cut by the mirror planes, but that's more physics than mathematics. So the question is, what happens if I change this angle? So let me make this angle a little bit smaller, and now something interesting happens here. If you make it a little bit smaller, then this image here breaks apart. So these parts no longer fit together in a good way to fill the entire plane. And if you really do it in the real world, what happens is you get situations like what you see here in that picture. So the images that you see, they don't fit together nicely. So our 58.6 that you see here is not a good angle for reflection. So the question is, after 90 degrees, what is the next good angle? And well, the next good angle that you get is not with a 5-fold rotation, but with a 6-fold rotation. So the next good angle that you actually get is a 60-degree angle, and here again you have the real world experiment, and let's add the 60 degrees to our list of good angles. And you again see, if you make this angle now again a little bit smaller, things start to break up again, and you may ask, what is the next good angle? And you may already guess it, that the next good angle is 45 degrees. Now you should start to think, what do these angles have in common? So let's add 45 degrees to our list, and so on and so on. And when I say and so on and so on, I mean that the next good angle is not, as you may have guessed, 30 degrees. It's actually 36 degrees. And after that, you get an angle of 30 degrees, and you may now understand where this comes from. The first angle here is 180 divided by 2. 60 is 180 divided by 3. 45 is 180 divided by 4. 36 is 180 divided by 5, and 30 is 180 divided by 6. So actually you get 1, 2, 3, 4, 5, 6 copies within one such 180 degrees region. So the next angle will be kind of pretty skew. It's 180 divided by 7, which gives a number which doesn't look that nice. And then the next one will be 180 divided by 8. So the general rule here is you get 180 degrees divided by n, for n being a natural number. So whenever you have such an angle, then around such a corner, the mirror images close up in a good way. And now you remember the headline of the lecture today is Triangles and Tessellations. And what we now want to do, we want to form a pavement from triangles that fit together nicely. And for that, we need triangles that are good in exactly that sense that you see here. Triangles where all the corner angles are angles from our list of good angles. So one of them in Euclidean geometry that makes it is, for instance, 60, 60, 60. So what you need is every corner is a divisor of 180 degrees. And the sum of the angles in Euclidean geometry should be 180 degrees as well. So 60, 60, 60 works. And then there are two more. One is 90, 45, 45, and one is 90, 60, 30. And if you try to find any more, you only will find permutations of where you have which angles, but the shapes of triangles, which I would call good reflection triangles, are really those three that you see here. And as a matter of fact, these triangles were also known to Felix Klein and even people way earlier of that, because they are interesting because of the following fact: they are perfect triangles to create a kind of mosaic in the plane with similar copies of such triangles. And the reason why this works so nicely for these triangles is that around every corner you fit around perfectly. So here you have the 45 degrees and you get all together 8 copies around one of those corners. Here you have the 90 degrees and you get 4 copies here, and so on. And actually I call it reflection groups because you can create such patterns by placing mirrors at the sides of such a triangle, and do the rest by well, taking the mirror images. And actually this is a reason, since we are focusing here on reflection groups, that I'm considering divisors of 180 degrees and not of 360 degrees, because you want to be able to generate that from reflections, which actually turns into the fact that you get a kind of white and black coloring of your mosaic. And so you see here the 90 45 45, here you see the 60 60 60, and here you see the more exotic one here, the 90 60 30. And that you believe me that these are really triangle reflection groups. Here is a picture of things we have in our mass exhibition, the X Quadrat, where we really have 3 mirrors here in the right angle, and what you see here are reflection patterns under exactly these kind of triangles. So we want to talk about hyperbolic geometry. So why am I telling you facts about triangles in Euclidean geometry? Because I want to contrast that with the hyperbolic case. So we just learned that in hyperbolic geometry, the angle sum is less than 180 degrees. And the main restriction that we had for the Euclidean triangles was the fact that the angle sum has to be 180 degrees. So essentially what happens is that in the hyperbolic space there is more freedom for the choice of triangles. For instance, you can get triangles like that. So if you only have a first look at that, it may look like a Euclidean triangle, but it's actually not. If you look carefully, this side here is an arc that lies on a circle. It's slightly bent, and if you measure the angles here, I got 90 60 20 triangle. So this is a good angle that would not occur like that in Euclidean geometry. You have to bend at least one of the sides inwards to get such an angle, but still it's a good angle in our sense, and in hyperbolic geometry this perfectly makes sense. So you can take this triangle, this 90 60 20 triangle, and fill the space around this corner point here with altogether 18 copies of the triangle. And what you get here is something that looks like that. So these here are really hyperbolic reflections that go from here to here, from here to here, and so on and so on. And the fact that you had 20 degrees at that corner makes sure, since 20 degrees is obviously a divisor of 180 degrees, that if you go around once, everything fits together in the end. So you see how important it is for this game to have angle measurement that is elliptic, because this makes clear that you really can go around in circles and that you really have to care about things closing up at the very end. But now look at that. Here we have a corner which is 60 degrees. So actually around that corner you can fit together 6 copies of your triangle. And here, so this here was 60 degrees and this here was 90 degrees. So around that corner you can fit together 4 of the triangles, and you can go on and on and on, and at each triangle do the same thing, and what you end up with is a picture that looks like that. So if you repeatedly make hyperbolic reflections in those triangles, you will actually get a figure like that that completely fills the hyperbolic plane and consists out of triangles that all are exactly the same. So they don't look as if they were exactly the same. So those at the boundary look considerably smaller, but they only look so. So remember our hyperbolic measurement where we learned that things at the boundary somehow are actually way bigger than they appear. So in that picture here, with respect to hyperbolic measurement, each of the triangles has exactly the same size, and you can already calculate that now because I told you how to calculate the area of a triangle, and the area of a triangle is completely determined by its angles, and you see here in that case all triangles have exactly the same shape, so they have to have the same hyperbolic area. So you really get infinitely many possibilities now of forming such triangle reflection groups, and here I have a little animation of that. So what you can do with these sliders you have here, you can change the numbers that you have here, and these numbers are the divisors that you need for the 180 degrees. So if I start to move these sliders here, I for instance can move this slider here still a little bit down, I get a triangle with indices 2, 7 and 3, which means you have 7 pieces around this arc, you have 2 pieces around that arc, and you have 3 pieces around this arc here. So you really get 3 different vertices governed by these indices here. So if you do the calculation, you see the angles must be less than 180 degrees, which means if you take these divisors A, B and C, you must have something like 180 degrees divided by A, divided by D, divided by C, must be less than 180 degrees, which in turn is the same as saying that the sum of these reciprocal numbers should be smaller than 1, and you immediately see, well, if you are already smaller than 1, you can simply increase A, B or C and still be smaller than 1, so you really get infinitely many types, and let me show you at least a few of them. So let me for instance move from 2, 7, 3 to 7, 3, 2, which is actually the same thing with the same kind of triangle, but now in the geometry I've chosen the 7 here is in the center of the picture. Let me do a comparison to something very classical. You find pictures of that already, surprise, in the work of Felix Klein, and I'm really amazed about the precision with which these pictures here are drawn. But there are infinitely many others. Let me show you a few more. So what you now see next is 5, 4, 2. So here you have an angle that gives 5-fold rotation. So one way to count this index here is just to count the number of black triangles you get in that picture. So around that corner you have 5, around that corner you have 4, this is this 4 here, and around that corner you have 2. And I want to draw your attention to to one interesting thing. So if you look at that picture here, it's a kind of regular pentagon with all right angles. So you have a right-angled regular pentagon, and actually if you merge some of the triangles here, you see that you have a kind of tiling here consisting of many such right-angled pentagons. So I would be busy until the end of all days if I would mark all of them, but I want to mark at least a few of them so that you get the idea of that. So you can really use this kind of triangle patterns as a basics for more complex patterns like well, pavements out of regular pentagons. Here's another one. Here is a nice quadrangle that you get here. I take a 4-3-3, and if you look at that, this induces that there exists a quadrangle with 45 degrees at each of the corners. So you see, you are very flexible, and there are many examples here, infinitely many examples here. I want to draw one connection because it's another way of looking at it. When I was a little child, I very often took Pfennige. So at that time there weren't cents, but there were still Pfennige, and I laid out patterns with those pennies. And well, you all know that if you take one penny at the center and put pennies around it, at the end it closes up perfectly, and you can go on and on and on. But this is really a special thing for the Euclidean space. So as I said, you can go on and on and on, but if you would do the same thing in the hyperbolic plane, depending on the size of your initial penny, so these here are pennies in the hyperbolic plane, and so look at them from the Poincaré model, and you know circles in the Poincaré models are really circles that we see, and what happens is that 6 pennies around one central penny won't close up. You will get such a gap here, and depending on the size of your central penny here, this gap will be exactly big enough to fit in one more penny, or 2 more pennies, or 3, or 10, or 1 million, depending on the size of your initial penny. So if you make penny patterns in the hyperbolic plane, they will more or less look like that. If you choose a penny of the right size, then it may happen that around any penny you get 1, 2, 3, 4, 5, 6, 7 copies, no matter where you start. So let's take, for instance, this penny here as a start. So you have 1, 2, 3, 4, 5, 6, 7 copies. So you get interesting circle patterns out of pennies of the right size. And actually this is another way of thinking about it, because underlying this pattern there's actually a tessellation of triangles. So here you have a triangle, and here you have a triangle, and here you have one, here you have one, and so on. And so you see you have 7 equilateral triangles fitting around a point, and we saw that some things like that can happen in the hyperbolic space. So let me end this whole excursion by becoming a little bit arty. I'm pretty sure you all know the famous Dutch designer and graphics person MC Escher, and he worked a lot on pavements of the plane. So he generated patterns like, for instance, that here, where you have pictures of angels and demons fitting together in a seamless way, tiling the entire plane. And actually, one of the reasons why Escher cared about such tiling patterns was that he kind of was obsessed with infinity, and such a pattern here can continue infinitely forever. And but on the other hand, he always had the dream of bringing infinity to a finite situation. And at one point in his life, he got in contact with famous mathematician Harold Scott MacDonald Coxeter, which can be really called one of the really great geometers of the last century. And he told him that, for instance, in Klein's work, you find these kind of patterns, and actually Escher took this idea immediately, and without doing the mathematics behind it, just with his graphical eye, he produced pictures like that, and you will immediately recognize them as a kind of complex tiling in the hyperbolic space and hyperbolic plane in that case. And you should also have immediately in mind that you're not getting smaller and smaller and smaller towards the boundary. You're actually having a tiling where all the angels have the same size and the demons have similar size as well. Here is, well, a pattern that I've been drawing with my ornament drawing app iOrnament, where you can also access hyperbolic ornaments. And what you see here is an ornament, an ornamental pattern together with an infinite motion. And I promised you at some point, when we had those images of the clocks moving in Euclidean space, in elliptic space, that we will also see something similar like that in hyperbolic space. And this is the point where we see that. So what you see here is a kind of continuous hyperbolic movement, and you really should at every point have in mind that all the stars that you see in that picture have actually the same size. And here you see how you draw matter from things that are further away, and you draw it more and more in the center of the picture until you lose it again at the other side. So you should really pick, perhaps with your eye, one of those little stars and tracing it, and see how it at the very end vanishes at the other side as well. So please don't be confused. This is not an image of a rotating sphere or something like that. This is really a movement in the hyperbolic space. So you see, we can also generate well, patterns that are kind of freestyle artistically in the hyperbolic plane, and I really recommend have a look at the iOrnament drawing program for playing with that. Here is a little glimpse to a research project that we once did in our research group. We took Euclidean tilings generated by Escher, and well, had the aim of creating as perfect as possible hyperbolic versions of them. And actually, it's a quite subtle business to get from here to here with only as little distortion as possible from the Euclidean picture to the hyperbolic picture. And actually, I consider that we are able to do that as one of a really major breakthrough. And actually what you do here is a kind of conformal mapping with some disturbations at one of the corner points. So if you focus here at that point here in that picture, so you see 3 of the lizards meet in that point, whereas at the corresponding point here 4 of the lizards meet in one point. So actually, one interesting fact is, while it takes just 3 colors to make a nice coloring of that, you need 4 colors in the other pictures, so things really get pretty subtle here, and we're pretty proud that we are able to do that. Okay, finally, I want to compare once more the Beltrami-Klein model, which is this one here, and the Poincaré model, which is this one, to show you, well, again, the 2 advantages and disadvantages here. So here the triangles really look very different if you look at them depending on where they are. But on the other hand, the edges of the triangles are perfect straight lines. Whereas here the triangles look very, very similar, just changed in size and rotation depending on where they are, but the lines are really band arcs that you get here. And you see, as I mentioned very often, here you have way more space at the boundary and less space in the center. So if you compare that here, in that picture, the situation at the center is kind of blown up, and you see that, well, you see different structures in both of the pictures, and perhaps each of them has its own justification. Okay, we're done. This was the final and last slide of our projective geometry class. Quite a journey. We started at things like homogeneous coordinates, learned about projective scales, about algebraic curves, about incidence theorems, about conics, about all kinds of strange deformations in strange spaces. I'm happy that you stayed with me until this last lecture, and I hope that I could give you some feeling both for well, the mathematical importance of that field of mathematics, but also for its intrinsic beauty, that is a beauty on 2 different levels. It's a beauty on the levels of formulas, because the formulas are always very elegant, but also on the level of the pictures that come out from that, because, well, they govern lots of our visible universe. And so whenever you look at some building with a row of windows, you will see perspectively deformed scale, and whenever you look at a ball rotating, you see something like spherical geometry, and when you look at one of the more complex things that Escher did, you look at hyperbolic tilings. Yes, I hope you learned something. I had a lot of fun here in that class, although I never saw you. It was really fun, and if you have any questions, please feel free to contact me. See you, perhaps, in one of the other terms, face to face, in one of the other classes.